Okay, welcome back, welcome back. Just getting set up here a little bit. Bear with me for a moment while I get organized. Hopefully. Okay. Right. This electrical machines, part 3. I repeat, electrical machines, part 3. Okay. Electrical machine, part 3. Right. What are you doing? You're a bit far over, aren't you? Okay. Yeah. Excuse me. The capacitor start motor, capacitor start induction run. Normally perceived as being a wide-ranging industrial motor, the capacitor start motor is very similar to the split-phase motor. Indeed, it probably helps to think of this more as being a split-phase motor, but with an enhanced start winding that includes a capacitor in the current in the circuit to facilitate the start process. If we look at the photograph, we can see the capacitor mounted on top of the motor case. And this is your capacitor mounted on the top of the motor case, okay? This is where your three-phase system supply would come into, okay? In this motor, the start winding has a capacitor connected in series with it. And since this gives a phase difference of nearly 90 degrees between the two currents in the windings, the starting performance is improved. We can see this represented in the sine wave shown in figure 6.14. Okay, let me see if I can come down a little bit. Okay, yeah, I think we can do that. Here you are, okay? Strong magnetic field in the run winding, weak field in the start windings, okay? Strong magnetic field in the start winding, 90 degrees. Now, you'll notice that although we're looking at something similar, and you may have seen this graph previously, you'll notice that the angle is different. That is the notification. In the other section, we were looking at 30 degrees phase shift. Here we're looking at a 90 degrees phase shift. Okay, 90 degrees phase shift. Okay. Now figure 6.14 magnetic field in capacitor start motor. In this motor, the current through the run winding lags the supply voltage due to the high inductive reactance of this winding, while the current through the start winding leads the supply voltage due to the capacitive reactance of the capacitor. The phase displacement in the currents of the two windings is now approximately 90 degrees. And here's your start winding, and here's your capacitor, again controlled by your centrifugal switch. Okay. Figure 6.15 shows the winding connections for a capacitor start motor. Now the magnetic flux set up by two windings is much greater at starting than in the standard split phase motor, and this produces a greater starting torque. The typical starting torque for this type of motor is about 300% of full load torque, and a typical starting current is about 5 to 9 times the full load current. The capacitor start motor is more expensive than a comparable split phase design because of the additional cost of the capacitor, but the application range is much wider because of higher starting torque and lower starting current. Therefore, because of its improved starting ability, this type of motor is recommended for loads that are hard to start, so we see this type of motor used to drive equipment such as lathes, compressors and small conveyor systems. Okay. Now, I'm not going to highlight this one section because I think I've got to give a variety and a variation, taking people's preferences into consideration. Okay, so now, as with the standard split phase motor, the start windings and the capacitor are disconnected from the circuit by an automatic centrifugal switch when the motor reaches about 75% of its rated full load speed. And again, reversing the connection to the start winding will only change its polarity, although we may choose to reverse the polarity of the run winding instead. Right, permanent split capacitor, PSC motors. Permanent split capacitors, PSC motors, look exactly the same as capacitor start motors. However, a PSC motor does not have either a starting switch or a capacitor that is strictly used for starting. Instead, it has a run type capacitor permanently connected in series with the start winding, and the second winding is permanently connected to the power source. This makes the start winding an auxiliary winding once the motor reaches running speed. However, because the run capacitor must be designed for continuous use, it cannot provide the starting boost of a starting capacitor. Typical starting torque for this type of motor are low, from 30 to 150% of rated load. So these motors are not used in difficult starting applications. However, unlike the split phase motor, PSC motors have low starting currents, usually less than 200% of rated load current, making them excellent for applications with high cycle rates. PSC motors have several advantages. They need no starting mechanism and so can be reversed easily, and designs can easily be altered for use with speed controllers. They can also be designed for optimum efficiency and high power factor at rated load. Permanent split capacitor motors have a wide variety of applications depending on the design. These include fans, blowers with low starting torque, and intermittent cycling uses such as adjusting mechanisms, gate operators, and garage door openers, many of which also need instant reversing. And here you have your capacitor start, capacitor run motor. Okay, see if I can bring that into view any better. Okay, now it's taking me out. Now let me see if I can get this text any larger. Let me just try something. Bear with me for a second. Let me just try something. If I can bring this any larger. Okay, okay. Okay, so let me see. Won't bear with me for a second. Let me see if I can bring you into line to make sure that you. So let me just rewind you a little bit. I think. Okay. Let's bring you across. Okay. You see that in picture frame, in the frame. It's in frame. Let's go up. Make sure that I bring everything into frame. Okay. Okay, let me just go across and make sure I bring you the frame as well, fully in frame. Okay. And just go back a bit. Bring you the frame also as well. Okay. Okay. Just going to take you down. Okay. There's 12. Okay. Bring it back a little bit larger. And I'll take it down from there. Okay. Okay. Right, another advantage of this type of motor is that it can be designed for lower full load currents and higher efficiency, which means that it operates at a lower temperature than other single-phase motor types of comparable horsepower. Typical uses include woodworking machinery, air compressors, high-pressure water pumps, vacuum pumps, and other high-torque applications. Okay, let me just bring this across so you can see it in full. Okay. Okay. Now see here, we are now going into shaded pole motors. One final type of single-phase induction motor that is worthy of mention is the shaded pole type. We covered this last, as unlike all of the previous single-phase motors discussed, shaded pole motors have only one main winding and no start winding. Starting is by means of a continuous copper loop wound around a small section of each motor pole. This shades that portion of the pole, causing the magnetic field in the ringed area to lag the field in the non-ringed section. The reaction of the two fields then starts the shaft rotating. Because the shaded pole motor lacks a start winding, starting switch or capacitor, it is electrically simple and inexpensive. In addition, speed can be controlled merely by varying the voltage or through a multi-tap winding. The shaded pole motor has many positive features, but it also has several disadvantages. As the phase displacement is very small, it has a low starting torque, typically in the region of 25 to 75% of full load torque. Also, it is very inefficient, usually below 20%. Low initial costs make shaded pole motors suitable for light-duty applications such as multi-speed fans for household use and record turntables. Okay. Okay, this bit, look up shaded pole motors for yourselves. Try and get a figure on that. Okay. Now, what I'm looking at now, what I'm a little bit pulled here is that I thought I would have seen a shaded pole motor. Thought I had one in here, but anyway, look that up for yourselves. Be sure that you are familiar with the shaded pole motor, and you can see what they're trying to say. Okay. Motor construction. On completion of this topic area, the candidate will be able to identify the basic principles of motor construction. To help you understand how motors are put together, this section includes photographs and diagrams of the components used in motor construction. Okay. Goodness me, look at this here. Let me just make this smaller so we can get onto the screen. Okay. This is brilliant in this illustration. You can see the NCU driving ends here. Okay. Those would be your bearings here. Okay. Right. That's your main rotor here on shaft. Okay. That's your stator. Okay. The eye bolt is what you move the motor around on by a crane or a stacker truck. Okay. So you can see that there. Okay. Brilliant, brilliant. Let me just make sure I can get this all the way over to it's not. And let me make sure. Let's give you the time to view this yourselves. Okay. Good, good. And it's showing you the components of a three-phase squirrel cage induction motor. Okay. Right. Now here we have the single-phase induction motor. This motor consists of a laminated stator wound with single-phase windings, arranged for split-phase starting, and a cage rotor. The cage rotor is a laminated framework with lightly insulated longitudinal slots into which copper or aluminium bars are fitted. The bars are then connected together at their ends by metal ending rings. No electrical connections are made to the rotor. Okay. And here we are. Let me make sure I can get this into view for you, full view for you. I don't want you to miss anything out, of course. It's useful to extract this information for yourselves and make it your own, basically. So you can see that here already we have just the sheer magnetic effect of this causes this motor to rotate. It's quite an intriguing thing. It has always fascinated me how they do the winding for the field of the motor. It's okay, I was just trying to think of a company that I could remember that used to do a lot of electrical rewindings of motors. You used to have some massive motors that was burnt out. It made you wonder how these things even got burnt up, but the power and the sheer force of these motors and the current that they handle is tremendous. Cannot be underestimated in any way. Brilliant, excellent stuff, beautiful. Motor speed and slip calculations, speed of a motor. Okay, so here there are essentially two ways to express the speed of a motor. One, synchronous speed. For an AC motor, this is the speed of rotation of the stator's magnetic field. Consequently, this is really only a theoretical speed, as the rotor will always turn at a slightly slower rate. Actual speed, this is the speed at which the shaft rotates. The nameplate on most AC motors will give the actual motor speed rather than the synchronous speed. Because the synchronous speed refers to the magnetic rotation That's my analogy of it anyway. Okay. Now I'm not going to. Now the difference between the speed of the rotor and the synchronous speed of the rotating magnetic field is known as the slip, which can be expressed either as a unit or in percentage terms. Okay, this bit here I'll leave for you to read. I hope you can be able to read this. I hope anyway. Okay. Now remember, when a conductor passes at right angles through a magnetic field, current is induced into the conductor. The direction of the induced current will depend on the direction of movement of the conductor, and the strength of the current will be determined by the speed at which the conductor moves. Okay. Now let's go back up a little bit. Okay. So this is where I'm going to stop now. Okay. This is where I'm going to stop here. Okay. This is brilliant. So this is my stopping end now. Okay, I hope you found this useful. Have a good day. Let me just go back up. Okay then, thank you. Have a good day. Bye bye.